Hi, this is Mrs. Bazin, and in this section we're going to talk about enthalpies of formation, which is section 5.7. So what an enthalpy of formation is how much energy is required, what is the enthalpy change associated with a compound being formed from its elements. So an example of this, you can kind of see what this means, is if we took carbon plus oxygen to make CO2, that requires an enthalpy change of negative 393.5 kilojoules. So that's how much energy is released when CO2 is formed from its elements. So this value here is called an enthalpy of formation because it's how much energy is required for this compound to form from its elements. It could also be called an enthalpy of reaction because this is a chemical reaction. This value here comes from a reference table. So this is a value that you could get from the back of the book or a table that I'll give you in class. So this value is something we can look up. So this is an enthalpy of formation. So again, how much energy is required or how much energy is associated with a compound being formed from its elements. So here's a table or an excerpt from a table for the standard enthalpies of formation for some different compounds. So when you look at this delta H value here, a couple things to notice. One is that there's a little F there, and that stands for formation because we're talking about a compound being formed from its elements. The other thing to notice is this little circle here, and that's a naught sign. That stands for them being measured under standard conditions, which are 25 degrees Celsius and 1 atmosphere pressure. So unless it tells you otherwise, we're going to assume that these are all measured under standard conditions. So you can see some values here. You can also see that the state does make a difference. So when you're looking these things up, it does depend on what state you're in. So you want to make sure you pay attention to that as you're pulling these values from the back of the book. Okay, so the way this works is a little bit different application of Hess's law. So if we're looking at the calculation of delta H for this overall reaction, we can kind of think of this happening in 3 steps. Okay, so I'm going to go ahead and put all 3 steps up here, and then we're going to talk about them. Okay, so to get from C3H8 plus oxygen to CO2 and H2O, we're going to think of this happening in 3 stages here. So the first step is that the C3H8 is going to be broken down into carbon and hydrogen. So it's going to be broken apart into its elements. And then on the other side, over here, we've got carbon and oxygen coming together to make CO2. And then we have hydrogen and oxygen coming together to make H2O. So this particular substance is breaking down into its elements, and then on your products on the other side are forming from their elements. So if we don't know the intermediate steps, like we saw in the last application of Hess's law, and we just assume that all of these new compounds are forming from their elements, we can use the heats of formation to come up with the overall heat of reaction. So this is how we're going to use Hess's law at this point. So the overall enthalpy of reaction is the sum of the heats of formation of all the products minus the sum of all the heats of formation of all of the reactants. Okay, so again, if we look at this formula for a second here, this little Greek symbol here is the summation. So that means you're going to add up all the heats of formation of the products, then you're going to subtract them from all the heats of formation of the reactants. So when I do this, I actually like to put brackets around this so we can kind of keep this separate. The other thing we have in here are these N and M variables here. What those stand for are the coefficients, because like we've talked about before, those delta H values are per however many moles are in that particular reaction. So if there's a coefficient in front of it, we have to take into account that when we're calculating the overall delta H. Okay, so let's do a couple example problems here. So here's my first example problem. So just like all of these other ones, we have to start with a balanced equation. Okay, so when you balance this, you've got C6H6 plus O2 yields CO2 and H2O. So if we balance this the way we've been doing it all along here, we would end up with 2 C2H2, 15 O2, 12 CO2, and 6 H2O. Now this particular question is asking for what's the standard enthalpy change per 1 mole? Now I could do this 2 different ways. I could go ahead and calculate it and then divide my answer by 2 because this is balanced per 2 moles, or I could take this down so that this is only 1 mole. So like we said, we're allowed to use fractions when we balance reactions for thermochemistry. So I'm going to say 15 halves O2 because I'm going to divide everything by 2, so I end up with a 1 coefficient in the front here. 6 CO2 plus 3 H2O. Okay, so that's my overall balance equation. So now I'm going to calculate my delta H of reaction here. So I'm going to take the sum of all the heats of formation of my products minus the sum of all my heats of formation of my reactants. So products minus reactants. All of these heats of formation values I'm going to get from a table. So I don't have that table here, so these numbers that I'm putting in here are being pulled from that table in the back of the book. Okay, so I have 6 CO2, so I'm going to take 6 times negative 393.5 kilojoules plus, so that's where that 6 came from, plus 3 times negative 285.8 kilojoules for water. So those are my reactants. So my products minus my reactants over here. So 1 times 49.0 kilojoules plus, down here, 15 halves times 0, because it's an element by itself. That's my oxygen. I'm going to add all that up. My overall heat of reaction here is negative 3267 kilojoules. Okay, so again, all the heats of formation of the products minus all the heats of formation of the reactants. All right, next slide is another one just like it. So if you are good with this, you can go ahead and skip ahead to the next one. But if you want to see another one, here's another example. Okay, so this time, standard enthalpy change for the combustion, again, of 1 mole of ethane. So I'm going to go ahead and write out my balanced equation, C2H5OH plus O2 yields CO2 plus H2O. When I balance that, I end up with 1, 3, 2, 3. So you don't end up with fractions like we did in the last one. I'm going to take the overall heat of reaction, or the overall heat of reaction equals heats of formation of all my products minus reactants. So I have 2 CO2s, so 2 times negative 393.5 kilojoules, and again, these numbers here are coming from a table in the back of the book, plus 3 times water, negative 285.8. So those are my products minus reactants. So I have 1 times negative 277.7 plus 3 times 0. Okay, when I add all that up, my overall delta H is negative 1,367 kilojoules. Okay, so the only other way you could potentially see these problems is because you won't have access to the table necessarily for tests and things. Usually they'll just give you what you need to know for that particular problem. So another way that these problems can present themselves is they can give you the overall enthalpy change and then some of the enthalpy, the formation enthalpies for some of the reactants and products, and then have you solve for the one that's missing. Okay, so this is what this would look like. So we want to know enthalpy change for the reaction below, and the reaction is missing here, so I'm going to write that in. So CaCO3, solid. And you'll need the states of matter for all these. Now I skipped those a little bit when I was doing those example problems, but when you have these, you'll and you work these problems, you'll be given all those, because those are important to make sure you pick the right value from that table. Okay, so here's the reaction here. So what they tell us is the overall for the whole reaction. We want to know what is the enthalpy of formation for this value here. So if this was given as a problem, you wouldn't be given that table, so you wouldn't have access to that value, but you would be given the other two. So let's write out our overall reactions here. So overall delta H equals the heat of formation of CaO plus heat of formation of CO2 minus the heat of formation of CaCO3. And these are all heats of formation here. Okay, so what they're asking me to find here is this value here. So this would be the one I don't know. I'd be given those other two. Okay, so let me switch back colors here. So they gave me the overall delta H of reaction. So that comes from up here. So 178.1 kilojoules. They would also give me these values here. So this would be 1 times negative 635.5 plus 1 times negative 393.5 minus the one I'm trying to find. So basically this is just an algebra problem where you just have to solve for this particular substance here. Be really careful with the math on these, especially with adding and subtracting the plus and the minus values. That's usually where people have issues with this. So be extra careful with that. And if we solve for the heat of formation, that ends up being negative 1,207 kilojoules. So again, I'm moving all of this to one side so that this is by itself, and that's my overall value.